Okay, hey. Good morning. Good morning, everybody. Welcome back to Data 100. Congratulations on making it to the last real lecture for the semester. This is the last lecture where we'll actually have technical content, so I want to congratulate you on making it this far. So I'm trying to make today's lecture light, and tomorrow's lecture will be we'll be having some people from the Division of Data Science come in to talk to us about ethical considerations in data science. And they have some activities planned for the first half of class. And in the second half of class, I'm planning to give a recap of everything that we've done in the course so far, and then maybe leave you with some life advice if I feel like it. Okay, so Project 3 is out and due Tuesday. Again, our final is taking place next Thursday. Here are the details. If you have special accommodations for the final, like if you filled out that request form at the beginning of the semester, we'll email you soon, but we're still working on getting the room set up and all the scheduling things worked out for the final. So we're working on it, but you should get an email soon. And we'll let you know when we sent out the emails so that if you didn't get an email from us, you can email us again and request that we look into your case. Okay, tomorrow is our very last lecture for the class. Again, Monday and Tuesday of next week will be a final review. And then Wednesday we won't have a class, and then Thursday will be our final. So tomorrow will be our last quote unquote lecture for the class. Today will be our last serious lecture for the class. Okay, so let's talk about random forests. Yesterday we looked at decision trees, and we saw that the problem with decision trees is that one requirement for fitting a decision tree is that all the nodes in the decision tree are pure. The problem with making the nodes in the decision tree pure is that when you do that, you're going to overfit your data because every single abnormality in your data will be captured by a decision tree via a really small rule for that particular data point. For example, you can see in this plot over here, even though there's only one orange point here, the decision tree decides to make this whole region orange in order to capture this one orange point here. And that's a sure sign of overfitting. In other words, decision trees by themselves have low model bias and high model variance. That also means that if I change my data set a little bit, or in other words, if I take another sample from the population and it looks even slightly different from my current data set, I might get a very different looking decision tree. And you can imagine why that might be the case. If I make a small change in my data, if that first split at the very top of that decision tree uses a different feature, now I'm going to have a very different looking decision tree. So this high variance hampers decision trees' ability to model patterns in our data. And I talked to you about briefly a few ways of approaching this. So one natural way to kind of solve this or to approach the model variance problem for decision trees is to say, okay, we're only going to go 5 levels deep, right? So I'm only going to grow my tree so far, and if I don't let it grow all the way down, then I shouldn't capture all of these little orange points here. I'll have bigger nodes that have some mix of blue and orange points, but at least it won't overfit my data as much. Another way of avoiding overfitting is to prune the tree, which means to let it grow all the way, but then use cross-validation to combine nodes together so that you get rid of some of the variance down here. So when it comes to using a single decision tree, people actually prefer the pruning method. But today I'm going to talk to you about another method that makes a nifty use of the bootstrap. And the idea here is we will bootstrap, fit many decision trees on each resample, and then take the average over decision trees, and that will be our final classifier, or final modeling algorithm. Okay, so it's pretty clever. And it turns out that this type of thing has a name. It's called bagging. It's short for bootstrap aggregating, which means you bootstrap, fit a bunch of models, and then aggregate all the models together. The idea here is, again, resample the data, fit one model for each resample, and what you do is when your final prediction is the average over all your models. It was invented by a professor here in stats named Leo Bremen in 1994. He actually retired in 1993, but went on to do his best work right after he retired. maybe after he got freed from his professor life, he decided to like, maybe he just like got a spark of creativity after he retired. Who knows? Anyway, it's a cool idea, and I'll show you how it works. Okay, so I have here some toy data, and the data look like this. Here we go. So I have here just data in a concentric circle. Okay, now what would logistic regression do for this data? It'd probably just fit some line, right? But the line would be like pretty terrible, right? It would probably go either like diagonally upward here or diagonally downward here. And you'd probably expect a classification error of like 50% if you're using logistic regression. Okay, so let's take a look at my data here. So what I've done here is I've split apart a training set and a testing set. And I'm going to, for now, fit a single decision tree and let it grow all the way down. So scikit-learn has decision trees built in. It's kind of fun to implement yourself, so I do recommend you try it out. It's just like how do I explain this? It's a recursive algorithm, and the thing about recursive algorithms is that when they work, they seem magical. So if you want to try it out, I encourage you to do so. Here we go. Fit the decision tree on my data, as usual. And I'm going to show you the score on the training set. Now, what should my score be? Score will be 1, because the tree grows all the way until it classifies every point in my training set correctly. But the score on the test set will be much worse. It'll be like 75% accurate. So that's a drop of 25%, pretty sizable. Okay, I can also show you that decision boundary on the training set. There it is. And you see here again, our familiar pattern of overfitting. We have like all these little regions of orange here. There's a weird region up here. Looks pretty messy. Looks like it's overfitting. Okay. So scikit-learn also has a bagging classifier. And what the bagging classifier will do is run the bootstrap underneath the hood and fit a bunch of decision trees to our data. So let's call this the bagging classifier. And I'm going to give it the decision tree classifier. I want to fit 100 decision trees. And I'll do this over 4 cores. Now it turns out that in scikit-learn, some algorithms come built in with a bit of parallelism. And so in this case, what I'm doing here is I'm not using Ray or Spark to do some parallelism. Because this bagging tree classifier can fit all the decision trees in parallel, and I have 4 cores on my computer, usually I can just say, here, I'll use 4 jobs to run this algorithm, which means it'll run this algorithm in parallel over all 4 of my cores. So it's like a little bit of parallelism that happens to work out nicely for fitting classifiers, sometimes. Okay, but anyway, I'm going to fit this classifier on my data and then show you the score on my training set. So it'll take a little while. It'll take a little longer because it's fitting 100 decision trees instead of just 1. And we see that indeed there are a few points that are not classified correctly, but it does do better on my test set. There's X test, here's Y test. So instead of 75% accurate, we get 80% accurate. So it does do a little better than before, and we can visualize this. Let's take the code up here and pass in my bagging classifier. And we see here that the decision boundary is indeed a little nicer than it was before. Okay, and the reason why it's nicer is because we are taking the average over many decision trees. So ideally, by averaging many decision trees together, we reduce some of the variability that each decision tree has. And if we bootstrap the data, then what happens is every sample looks a bit different, so every decision tree makes a slightly different prediction, and taking the average over those predictions gives us a smoother decision boundary and reduces overfitting. Now it's not perfect, right? So you can see here that there's still, it's not like the ideal decision boundary that we would like, which is like one smooth circle here. There are ways of addressing this too, but in reality, what we'll do is we won't actually use a bagging classifier. We'll make one more extension to decision trees, and that's what we'll call a random forest. Okay, so it turns out that if you just bag your data, oftentimes for a decision tree at least, it's not enough to reduce model variance. It's not enough to reduce model variance and actually avoid overfitting. And the reason why it's not enough is because when you bootstrap your sample data, the decision trees will still look very similar to each other. So for example, you can imagine for your email project, right? If you bootstrap your sample data, your sample emails, if Viagra was like the very first split at the top of the decision tree, even if you bootstrap your sample data, Viagra will still be the very first split at the top of the decision tree. Okay, so if you do that, your decision trees will look slightly different, but oftentimes you want to make them look more different from each other because you want more variability in decision trees. Okay, so the idea here is bag the sample data, but also don't use all the features when you make a split, only use a small subset of them. So instead of using all 100 features for deciding what split to take at a node in the decision tree, I'm only going to use, let's say, 30. And the rule of thumb here is that usually, if you set the number to square root of p for classification or p divided by 3 for regression, your decision tree will do pretty well. Okay, so this means that if I have 100 features to start off with, if I use this rule for classification, I'm only going to consider 10 rules, or 10 features at every time I split a node, instead of all 100. The idea here, again, is we want to average together many decision trees, but we want each decision tree within this forest to overfit in a different way. And if they overfit in a different way, when you average them together, the overall forest will have low variance. So again, the neat thing about a random forest is that when you have multiple trees, it's a forest, get it? And it's random because you're bootstrapping, and you're also selecting these m features at random at each split. So it's like a tree, it's like a bunch of trees in a forest, and it's random. Okay, so it's kind of neat. And I have a note here, which is that. So I'm saying these things, and you might question why we want our individual trees to be more different from each other, and why that reduces the variance of the random forest. And the reason why it works out is because if the trees all look alike, when you average them together, the average will still have high variance. Okay, but if the trees are all varying but in different ways from each other, then when you take the average, sometimes you can imagine a tree being too positive sometimes and a tree being too negative some other times. But if you average the positive trees and negative trees together, you should get something close to 0. I'm just giving you a hand-wavy explanation. But if all the trees are always positive, or if all the trees are always negative, then even when you average them together, you won't get 0. That's kind of the hand-wavy explanation for this. But I do encourage you to kind of feel this idea out a little more on your own time and try to understand why you want to, what we call, decorrelate these trees. We want these trees to be different, but we want them to be smart in their own way, but different from each other, so we can take the average and get a good result. Okay, but this gives us the algorithm for random forests, which is the following. We bootstrap the training data t times, and for each resample, we'll fit a decision tree. Again, this is a decision tree fitting algorithm, so we'll start with all the data in one node, repeat the following until all nodes are pure. We'll pick an impure node, but the difference here is that we'll pick, instead of looking at all the features, we'll look at a random subset of m features. And each time we do a split, we'll find the feature j and value theta within these m features that minimize the loss, instead of looking at all the features. We'll split the thing into 2 nodes, and we'll repeat that. Once we fit all the decision trees, to make a prediction, we'll ask all the decision trees for their predictions, and then take a majority vote. So pretty similar to fitting a decision tree, except that we fit many of them, and we use a subset of m features instead of all the features we have available. Okay, any questions about this? Okay, pretty cool stuff. So one thing you should go back home and try to understand here is how do t and m in this algorithm affect the bias variance trade-off? Okay, so if you increase t and increase m, you will either increase bias or variance and decrease the other. And you should try to think about which ones affect what and why. But I want to show you how random forests work, so let's do it. Okay, so scikit-learn also has a random forest classifier, conveniently enough, and I'm going to fit it. So here it is. I'm going to fit 100 trees. I'm going to use entropy metric, and I want to split this across 4 cores. There it is. I'm going to fit this on my training data and compute the score. There it is. And managed to get 100% training accuracy, but it does get better test accuracy than my original decision tree. Oops, my bad. There it is. So it's roughly equal to the bagging classifier. And if I look at that decision boundary, okay, so here we go. We looked at the decision tree. Here is a test error, or here's a test accuracy, which is about 76%. We looked at the bagging classifier, which has a test accuracy of 80%. And we looked at the random forest, which has a slightly larger test accuracy of 81%. I would say this is probably equal to the bagging classifier. And in fact, if I look at that decision boundary for the random forest, you'll notice that the decision boundary looks pretty similar to that of the bagging classifier. And in fact, the decision boundary here is still kind of jagged and rough. So why didn't the random forest do better than the bagging classifier for this case? It has to do with the fact that in this particular example, I only have 2 features. And the random forest, since it doesn't look at all the features, but since there's only 2 features total, it'll just pick 1 feature at random out of my 2 features and split on that feature. And so really, the random forest and the bagging classifier look pretty similar to each other because we didn't have that many features to start off with. So by selecting a subset of features, the trees still look mostly the same. Okay, so in this particular 2-dimensional case, I wouldn't expect to see a real difference between the random forest classifier and a bagging classifier. But I can now do something that has more features and see how the random forest does for this case. Okay, so what I have here is some image data. This image data is people writing digits on a piece of paper, and then the computer scan those digits. Okay, so what I'm going to do here is take a look at this data frame. This data frame has 60,000 digits, and the way I've encoded this data is every image is, I believe, a 28 by 28 pixel image, and I've just put all the pixel values inside of each row of my data frame here. In other words, if I display some digits, let's take every 6,000, wow, that's hard to say. Every 6,000 digits and display them. Okay, so in my data set here, I have some digits, and every digit is encoded as just like a sequence of pixel values, but if I put the pixel values in a grid and then color code them by how big the values are, then I'll get like nice patterns like this. Okay, so the task here is take these images and decide what number they are. And the reason why I might want to do that is because, for example, when you write a letter and you send it out in the mail, the postal office will use something like this to decide what zip code is in that mail. So before they had algorithms like this, they'd have to have someone in the post office read that mail and enter in a computer and manually copy over that number into a computer. And now what they do is they just automatically read in that zip code from like handwritten mail. This is also how they read in, I believe, like numbers written on checks, for example. So if you write a check, you're paying for rent, you'll like handwrite that number onto your check. And what the bank will do is automatically read in those numbers using this sort of algorithm here. So the idea, so the goal here is take the image data and predict a digit from 1 through 0, or 0 through 9, because we have 10 possible digits to predict. Okie dokes. So I can just try using logistic regression on this. Well, let's try it out. So here we go, logistic regression. And it turns out that the LBF-GS algorithm is a little bit faster than using Saga for this, so I'm just going to do this to save time. What I really want to show here is that the logistic regression algorithm doesn't do that well. And the reason why it doesn't do that well is, well, one reason is I'll just give you like tons of warnings. So I have like 10 warnings here. There we go. Okay, I look at the score. It got about 95% accurate on the training set, but on the test set, it gets about 85% accurate. So a pretty significant accuracy drop. And what I can do here is, oftentimes when I have classification, I want to make a confusion matrix. And so what I can do is make the confusion matrix. By the way, on the project 2, if you didn't make a confusion matrix, I suggest you try it out next time, because I noticed that some people, their classifiers would just always predict spam, or always predict not ham, or always predict ham. And the way you diagnose those problems is not by looking at your accuracy, but by applying the confusion matrix and seeing like which cells in that confusion matrix are shaded in. Okay, so in this case, what I'm going to do here is plot the confusion matrix y test and the predictions on my test set. And I'm going to divide by the length of y test to normalize all of the numbers here. Make a heat map. And I'm going to use a blue color scheme because I like the color blue. Like so. Okay. Now we have 10 rows and 10 columns. Why is that? We have 10 rows and 10 columns because we have 10 possible classes to choose from instead of 2. This is not a binary classification problem, it's a multi-class classification problem. There are 10 possible labels for every point in my data, and because of that, my confusion matrix has 10 rows and 10 columns. Okay? Now we can see here that the logistic regression classifier does pretty well. So we see here a line of a darkly shaded diagonal line, which means that, for example, most of the time it was able to label a 9 as a 9, most of the time it was able to label an 8 as an 8, so on and so forth. But what types of labels did it have the most trouble on? It's a little bit hard to see from this plot, right, because these diagonals are so dark. You can kind of tell that the 5s were not predicted that well, and maybe the 8s, but the 1s here are predicted quite well. And so what I'm going to do here is I'm going to zero out this diagonal, and that will make Seaborn like automatically recolor the rest of the squares so we can see which ones are darker than the others. Okay, so I'm going to fill diagonal with null values, and then remake this confusion matrix. Okay, so this is the same matrix as before, but the diagonals are all 0, so we can see the rest of the values that are off the diagonal. And so how do we interpret this? Well, we interpret this as saying, if you have darkly shaded squares, that means that you have bad predictions, right? So here, on this column, the 8s seem to be often predicted as a 2 from my model. The 5s are often predicted as 8s. The 3s are often predicted as 5s. So that's how I would interpret this confusion matrix. It might make sense if you look at the data. So if you actually look at the values inside of this block here, you might see people who have some messy handwriting. And when you have messy handwriting, sometimes your 5s can look pretty close to an 8. That seems pretty natural. But the way you would check that, right, is by going into your data and actually looking at some of those images that you didn't classify correctly and seeing if you can improve your classifier via some feature engineering, for example, or tuning the regularization amount, the usual deal. Okay. But in any case, what I want to do here is show you the random forest classifier. Here's a forest. Let's call it RF. And I'm going to give it, again, 100 trees. And run it in parallel over 4 cores. Okay, and I'm going to fit this on my training data as usual. I put this time magic, which is useful if you want to figure out how long a cell will take to run. So you can run it once, and you see that it takes 3 seconds. If it takes 3 minutes, again, I can know, roughly speaking, how long it'll take. So I know, if I run this again, I want to fit my model again, I can get up and get a drink of water and then come back. All right. If I increase the number of estimators from 100 to 1,000, you might expect the runtime to increase by a factor of 10. So if I go from 100 to 1,000, I might say, okay, well, that's still pretty reasonable. That'll take about 30 seconds to fit instead of 3 seconds, but I feel like I can wait 3 seconds. With random forests, sometimes sometimes your model still gets more accurate even as you go into thousands of trees or 10,000s of trees. So oftentimes it's useful to fit it on a small number of trees and increase the number of trees in your forest until you're unhappy with the runtime, because oftentimes it does help with the accuracy. In any case, I'm going to show you the training error. Here's a training error. Got everything right. And the test error. Okay, so my logistic regression got, let's take a look here, about 85% right on the test set. The random forest gets about 94%. So it's an increase of about 10%, which is pretty sizable. And I did that not by doing some fancy feature engineering, but just by choosing a better model. And as before, I can show you the confusion matrix. So let's copy that, paste it here, and show you that confusion matrix. So again, it looks mostly the same. But if I zero out the diagonal and show you what that looks like, we see here that there are less darkly shaded squares than there were for logistic regression. But it does look like the types of errors that the random forest makes are different than the logistic regression classifier. So it sometimes predicts 9 as a 4, and sometimes predicts 5 as a 3, but it doesn't make the same mistake of predicting 5 as an 8, interestingly enough. So you can go deeper into these models and try to figure out why. And usually what you want to do to actually improve a model is use tools like the confusion matrix or a learning curve to diagnose the problems, and then see if you can improve the model by specifically tackling these problems. So for example, if you notice that 5s look close to 3s, what you might want to do is try to create or do some feature engineering that you think will distinguish 5s and 3s from each other. Or you could do the same thing for 9s and 4s. And usually what you want to do is you fit a model and then diagnose problems and then iterate on the model until you get a good accuracy. Okay. Another thing you can do is apply the same averaging method across multiple different types of classifiers. So if I notice that the logistic regression model and the random forest model are making the errors on different digits, I could imagine a case where I bootstrap my data and fit a bunch of logistic regression models and fit a bunch of random forests, and then my prediction is the average of both logistic regression models and random forests. So those types of methods are called ensemble methods, and they turn out to be pretty good. So I believe a few years ago, there was a competition run by Netflix, and they offered a prize of $1 million to the team that could increase their recommendation, that could increase the accuracy of the recommendation algorithm. So if you're on Netflix and you're watching a TV show, they'll give you a recommendation for the next show you watch, and some of you know how scarily good that algorithm can be. And the way they were always trying to improve the algorithm, and so they offered a prize, and he said, I think if you can increase the amount of click-throughs on the recommendation by 5%, they'll pay you $1 million. And the team that won, so actually the story of what happened was there were two teams, two big teams that were applying tons of ensemble methods to the problem, and they were in the top 2. And then one team said to the other, well, we don't want to compete with you, actually. How about we just join forces and split the money? So I joined forces and split the money, and everyone was pretty happy. It turns out, sadly, that Netflix, I don't think Netflix actually used that algorithm in the end because of some runtime considerations. But it's an interesting example of how ensemble methods can be useful in real life. Okay. So that's random forest. Why do we teach it? Well, it's a versatile algorithm, so you can do the same algorithm for both regression and classification. It's invariant to feature scaling and translation, which means so for logistic regression, I have to be careful to normalize my features before I put it into my classifier, and especially have to normalize them if I have regularization in my model, right? But a random forest doesn't really care about feature scaling because it just makes decision rules based on the values within the feature and not how the features relate to each other. If I shift my data around, so if I take all the values in one column and add 10 to all the values, random forest will still be pretty happy about that. It'll just make different decision rules at every branch in the tree. It does automatic feature selection, which means that if a feature is completely useless, it just won't be put in the decision tree. It just won't be used at all. And so you can tell from the random forest what features are useful and what features are not. There are actually ways of scoring the features to say which ones are more, to give them a numeric score of how useful they are. But we won't go over that in this class. You can look over how to do that if you go deeper into random forests. Okay. They give you nonlinear decision boundaries without having to do some complicated feature engineering. So you saw how I was able to fit that circle, right, the circle of points with the random forest out of the box without having to do some complicated polynomial features that I would have to do for logistic regression. The nice thing about them also is that they don't overfit as often as other nonlinear models like polynomial features, because we have the advantage of being able to average over many trees. It's an example of the ensemble method of combining models together to get a better model overall, and an example of using the bootstrap to reduce model variance. Okay. The downside, of course, is that a random forest will take longer to fit and longer to make a prediction than a decision tree, right? Because if I want to fit 1,000 decision trees in my forest, my fitting time will increase by 1,000. And if I want to make a prediction with 1,000 trees in my forest, making that prediction will take 1,000 times as long. The other downside is the interpretability of that random forest. So if I gave you a decision tree, you could probably interpret what the decision tree is doing. You just follow the branches and say, okay, this model says if it's before 10 a.m., Sam is going to take the BART, otherwise he's going to drive. But a random forest, because you have 1,000 trees in that forest, it becomes harder to really understand what that model is doing. But the trade-off here is that usually you can get a much more accurate model at the expense of some interpretability. So in every situation, you should try to figure out how much interpretability you want, how big your data are, what are your limits on runtime, what kinds of accuracy you want to achieve, whether or not you care more about false positives or false negatives. And you should use all those factors in consideration when fitting a model and using a model rather than just fitting 10 models blindly and picking the one with the lowest validation error. Okay. Any questions about that? All right, let's take a break. And open it up. All right, go for it. We'll come back here in 3 minutes. Okay, let's bring it back. Is anyone still filling out attendance? Okay, give you a few more minutes. Okay. So again, I want to congratulate you on finishing Project 2. Project 2 is one of the most open-ended assignments in the class because we give you the setup to fit a model, but all the improvements to the model you had to kind of dream up yourself and do it yourself. And so I hope it was interesting and fun, and it's a real problem, right? Predicting email spam is a real problem that Gmail and other email providers use all the time to decide whether email should go in your inbox or not. And I think, let's see. So it turns out that you can do pretty well on that problem by doing something relatively simple. So I was just messing around with the data yesterday, and I think what I did was I just took all the words in the data set, took out all the punctuation, split everything up by spaces. So I had like a list of 100 or 200,000 words, and then I sampled 500 at random, fit logistic regression, and got like 98% accurate on the test set, and then like 99 using a random forest. So oftentimes you can do pretty well by just throwing all the data that you have at your classifiers and just trying to see how well you can do. In any case, the reason why I wasn't able to use all 100,000 words, which I could have, right? If I had like a huge machine or like I had distributed computing, I could in theory use like 100,000 words for a classifier. But the reason why I couldn't do that is because of runtime considerations. And it turns out that if you want to fit a model, oftentimes what you're concerned about is you'll run your code and your cell will just remain running for a long time, and you'll have no idea how long it'll take to run. And the problem is sometimes your cell will take like a few minutes to run, and sometimes it'll take a few days to run. Okay, so it's important to be able to estimate, like ballpark estimate, how fast or how long it will take a cell to run. And the way we characterize those decisions is via runtime analysis. So it's a little review from 61A, but I did want to apply it, especially to modeling, because it comes up quite often it comes up quite often even when you're working with relatively small data sets like that email data set. So even though the email data set only had a couple of thousand examples, if I wanted to use every single available word within that data set, I would quickly get a model with like 100,000 features, and it would take too long to fit a model. Okay, so here's the notation. If we have a training matrix or design matrix X and it has n rows and p columns, what we'll do is use what we call big O notation to describe the runtimes. So in 61A, we use theta. In this class, we'll use big O, but for the purposes of our discussion, we can treat big O and theta the same. And the reason why I use O instead of theta is mostly just because I can type O on the keyboard instead of using theta. But really, in this class, they're about the same. If you want to know the real difference between theta and O, you should take 61B and CS170. Okay, now, if I write that an algorithm takes O of n times p time, what I mean by that is if I double the number of sample points, I'm going to double the runtime of this algorithm, roughly speaking. Also, if I double the number of features, I'm also going to double the runtime, because this algorithm here is linear in both number of features and the number of sample points. Okay. Now, if I write an algorithm takes O of n squared time, if I double the number of sample points, I'm going to increase my runtime by a factor of 4. So if I had an algorithm that took 1 second to finish, if I double my data set size, now that algorithm is going to take 4 seconds to finish. And the difference between a linear time algorithm like the one here and a quadratic time algorithm like the one here can sometimes be very large, especially when working with larger scale data sets. Basically, if you come across an algorithm that takes quadratic time or higher, you just can't use it in real life. Because as soon as you get to any data set of meaningful or useful size, your algorithms will just take too long to run. Now, it's not always the case that you can't use quadratic time algorithms. You can use parallelism, for example, to reduce your runtime. But for this class, if you just imagine like trying to fit a classifier on your laptop, basically you can't use quadratic time algorithms. You have to use something faster than quadratic time. Okay. So I want to give you some practice, and this should be some review from Su19. So try this out. Find these runtimes. Find the runtime of looping through all the values in the data set, looping twice through all the values in the data set, taking the mean of each column, taking the means of all the columns in the data set, and doing a dot product with two length p vectors. All right, so try it out on a piece of paper, or if you're good at this stuff, do it in your head. But you might find it helpful to write it down, like write the O, parentheses, like stuff inside the O, and see if you can get these out. Just a little warm up. Go ahead. Oops. Okay, so once you have those down, see if you can find a neighbor and compare answers just to see if you get those right. Okay, dokes. So let's go over these together. Looping once through every point in a data set. Well, a data set has n rows and p columns, which means that there are n times p points. If you loop through all the points once, that will take O of np time. Now, if you loop twice, it will take O, well, we'll write down that if you loop through twice, it'll be 2 times n times p. But in big O notation, we don't include the constant in front of the variables here, so the total runtime is O of np. Both these algorithms are O of np. The reason why we don't care about this constant is because what this is describing is not how long it'll take to finish, but rather how long it'll take to finish compared to a bigger or smaller input size. So what I care about here is how much longer will it take if I double my input size, not how many seconds it'll take overall. The reason why both these have the same runtime is because if I double the number of points in my data set, or let's say I double the number of n, both these algorithms will take twice as long to run. Okay, taking the mean of a column, well, that involves looping down one column, which has n values, taking the sum of all the n values, and then taking the average, which is a constant time operation. That's O of n time. If I want to take the means of all the columns, then I repeat this operation once for all the columns. There are p columns, so the total runtime is O of n times p. If I have two length p vectors and I do a dot product, what I'm doing there is looping through p numbers and doing p multiplications and additions. And that will take O of p time. Okay. What I want to show you is, okay, so these are hard for you. You should go look at 61A and review that material. I put a link on the slide here. But all of this should be mostly review, hopefully, so I want to just refresh your memory. And what I want to do now is apply some of this notation to the algorithms that we've run in this class. So what I'll do is I will run through the algorithms and give you the runtimes. But what you should do is go back and try to work out and try to understand how I got those runtimes in the first place. I do want to start with the rule of thumb, which is a convenient tool that I use when I'm trying to figure out how long an algorithm will take to run. So very, very roughly speaking, vanilla Python code, like writing for loops, can do about 1 million calculations in a second. So if I have 1,000 rows and 10 columns in my data, then I would estimate that looping through all the data, or taking the mean of every column, or algorithms that in general take O of np time, will take about 10 seconds to run, right? Because we have 1 million rows, 10 columns, that's 10 million values. 10 million computations takes about 10 seconds to run. That's kind of like how I do my back of the envelope calculations. And it turns out that this is pretty accurate for most cases. Now, obviously, your laptop might be beefier than mine or slower than mine, and it'll take you a little bit more or less time. But what I'm trying to do here is decide between will it finish or will it not finish? Okay, and the difference between finishing and not finishing is quite large. For example, if I try to run an O of n squared algorithm, it'll take 11 days to finish instead of 10 seconds. All right, so the difference is quite vast. And knowing the runtimes can help you decide whether you should wait 10 seconds or 11 days. So the idea here is that if you run a cell, or if you're working through a data set and you notice it has a lot of rows and a lot of columns, you want to keep the runtimes of your algorithm in mind as you work through your data, so you can figure out whether your algorithm is going to finish or not. Now again, the 1 million calculations thing is just my rule of thumb. It's a personal rule that I use. You probably won't see it outside this class, but it gets close enough most of the time, and I'll show you what I mean. All right, so I have here a cell, and again, the time it magic will run the cell multiple times and compute the average time it took to run the cell. What I'm doing here is I have a million numbers, and I'm taking the squares of each number. So let's do that. If I run that cell, what happens is it'll take a million numbers, compute the squares of each one, and do that over and over again. And we see here that for a million calculations, it took me about half a second. So it's not exactly 1 second, but it's on the order of a second, like 1 second, between 100 milliseconds and between 10 seconds. Now, if I double my input size, so if I go from 1 million to 2 million, what do you expect to see as the runtime? Well, this algorithm is linear time, and so what I expect to see is that the runtime doubles, and we see that here. Okay, now if I wrote this, this right here is a quadratic time algorithm, and based on my calculations above, it will take me about a few days to run this, which is a long time. Don't want to actually run this. Now the thing about NumPy is that if you run operations in NumPy, things will generally run much faster. So I'm going to run this cell here. And it's the same thing as the one here, except using a NumPy A range instead of using a Python range. And we see here that it takes about 100, we have a speed up of about 100 times. So we go from 400 milliseconds to just 4.7 milliseconds. That's quite a speed up. And so if you can run your stuff in NumPy or via a pandas vectorized function, you should try to do that because it'll make life a lot faster for you. The thing about NumPy, though, is that it will not affect how your runtime grows. And this is why we care about using big O notation, because if I double n here and run the same algorithm, I still notice a doubling of runtime, no matter whether I use Python or NumPy. Okay, so NumPy will make the baseline code run faster, but it will not change the growth of that runtime as I increase n or as I increase p. So that's why I use the big O notation to describe code, because it will affect you no matter what types of algorithms you run or what types of optimizations you have, whether you're not using NumPy. Okay, so let's walk through some algorithms. So here's a gradient descent. How long does it take to compute the average gradient? That's supposed to show up one bullet point at a time. But I look at this equation here, and I say, okay, well, theta is length p, x of I is also length p. Doing a dot product between two length p vectors is O of p time. I have a p vector here, and that will take O of p time. So the inner sum here will be O of p. And since I'm doing the inner sum n times via the sum, the total time to compute the average gradient is n times p. It's a linear time algorithm in n and p. Okay, now, for gradient descent, we have to introduce a little bit of mathematical trick. Okay, so because gradient descent will approach the minimum of a function, but not get all the way to the minimum. What I'm going to say here is, I'm going to say epsilon is the desired error after running gradient descent. So if I say epsilon is 0.1, then I'm okay with stopping gradient descent once I get 0.1 away from the actual true minimum. If I let epsilon go smaller, I'm asking gradient descent to give me a more accurate result. And if I make epsilon go bigger, I'm saying I'm okay with getting an imprecise result from gradient descent. So you can imagine with me that if I want a really small epsilon, that's going to take me longer to run, because to get a more precise result will require more iterations of gradient descent. And if I have a very large epsilon, then I'll converge faster than I would before. So the idea here is, here we have batch gradient descent, and I'm not going to prove this to you. I'm just going to state that batch gradient descent will take about log of 1 over epsilon iterations to converge. Stochastic gradient descent, on the other hand, will take 1 over epsilon. And the way you should read that is, if I want to get very close to the minimum loss, I have to pay the price and do more iterations. So if I make this epsilon smaller, my runtime goes up for both batch gradient descent and stochastic gradient descent. But for stochastic gradient descent will take more iterations than batch gradient descent to converge because of this log right here. So the log in front of the batch gradient descent, 1 over epsilon here, will in general just make this much smaller than stochastic gradient descent. But you might say, well, I thought that we used stochastic gradient descent because it takes less time overall. And the reason why it takes less time overall is because each gradient calculation in batch gradient descent takes a lot longer to compute. Okay, so in batch gradient descent, we saw before that if you do the average gradient, that will take O of np time. O of np time per iteration, and if we have log of 1 over epsilon iterations, the overall runtime is this runtime multiplied by this runtime, which is np times log of 1 over epsilon. For stochastic gradient descent, it takes less time per iteration. It only takes O of p time per iteration because we're not doing the sum over n points. We're only computing the gradient for a single point. And so the overall runtime is the time it takes per iteration times the number of iterations we have, and the overall runtime there is p over epsilon. Okay, so because of the factor of n in batch gradient descent, usually batch gradient descent will just take a lot longer to run because n is oftentimes just really big. N is the number of points in my data, and we often work with data that have millions of points, or more than that. Okay, yeah, Jesse?
Why it is 1 over epsilon?
Why is stochastic gradient descent 1 over epsilon? It involves some complicated math that I won't go into. But essentially what you do is you say, how much do I improve my estimation every time I run an iteration of stochastic gradient descent? And then you essentially do a summation over every improvement until you get to the desired error. Yeah. Okay, what about cross-validation? So let's suppose that we run k-fold cross-validation for linear regression. What's the runtime? So we know that if you fit a linear model with gradient descent or stochastic gradient descent, it will take O of p over epsilon time. And in k-fold cross-validation, you fit k models, so the overall runtime of k-fold cross-validation is k times the time it takes to fit each model. It's k times p over epsilon. In other words, if I double the number of folds, I'll double my fitting time. Okay, what about decision trees? What's the runtime of making a prediction using a decision tree? So if I give a point, how long will the decision tree take to give it a label of driving or barding? Well, we have every rule here takes constant time to check. And how many rules can we check overall? That's going to be the depth of my decision tree. So it's going to be as far down as I can go on this decision tree until I have no more rules to check. That's what we call the maximum depth of a decision tree. And because there are a maximum of d rules to check, making a prediction from a decision tree takes O of d time. It turns out that because decision trees are fit using data, they're not, usually what happens is the tree kind of evens itself out and you have d is close to log of n. But sometimes you can get d is close to the actual value of n, so you can take a long time to run. So this is a difference here between, let's say you have 1,000,000 points in your data set. This right here is a difference between taking like 2 seconds to run and taking let's say a minute or so to run. Probably more than a minute in this case. Okay, so the difference here is quite big. Log n and n are quite far away from each other. But the nice thing is that usually we get d is close to log n. Only in some certain special cases do we get d is close to n, and you should try to work out on your own when you might get this instead of this. Okay, so what about random forests? Well, we have d as the depth of the tree. It turns out that fitting a decision tree takes n times p times d time. I'm not going to prove it to you, but it involves some nifty tricks around evaluating how long the rules take. Roughly speaking, it takes n times p time for every level of the decision tree. And because of that, because we have d levels of the tree, the overall runtime is n times p times d. Now, since d is close to log of n, we have here, it takes about n times p times log n time to fit the tree. That turned out to be pretty reasonable because log n is small. So we have something that's very close to a linear time algorithm for fitting a decision tree. That's why we can use it quite often. Now, because we fit t trees for a random forest, and it takes n times p times d time to fit each tree, the overall runtime for fitting a random forest is tnpd. All those things multiplied together. The time it takes to make a prediction from a random forest is t times the amount of time it takes a decision tree to make a prediction, which we saw on the last slide was O of d time. So the total time needed to make a prediction from a random forest is O of t times d. So you should think about these runtimes. I don't expect you to understand everything right now, but what you should do is go back to the first examples that I had on the previous few slides, walk through them, and then go back through the class as you're reviewing the material for the final and see if you can get the runtimes of every algorithm that we've talked about. Okay. Well, that's about it. So I want to give you an overview of everything we've learned in the second half of class. You actually learned quite a lot. Okay, so if I ask you, how do you estimate a population parameter, you would say, well, I would create an estimator, and I can analyze its bias and variance. And then I can create a bootstrap confidence interval for that parameter and give that to you as an estimate. If I ask you, how do you make predictions about numeric values, you would say, well, I can do regression. I can do linear regression, or decision trees, or random forests. If I say, I want you to predict for me categorical values, you would say, okay, well, that's not too bad either. I can give you logistic regression or decision trees and random forests. And I forgot to put in k nearest neighbors here, but if you remember k nearest neighbors from data 8, you can use k nearest neighbors here as well. All right? How do you fit a model? You would say, well, I would find the gradient of my loss, and then I can run stochastic gradient descent to fit the model. If I ask you, how do you know if your model is doing well, you would say, oh, that's easy. I'll do cross-validation. And I can plot the validation or learning curves, and I can plot the confusion matrix and ROC curves for classification. If I ask you, okay, well, improve your model, you would say, well, I would do some feature engineering, or I can adjust regularization, or I can adjust other hyperparameters, like the number of trees in a random forest. So I want to give you, oh, here's one more. Okay. So why do some models do better than others? We know the bias variance trade-off and how it describes why some models are better than others for a particular data. If I ask you why some models run faster than others or fit faster than others, you could do some runtime analysis on that model and tell me whether a model will take longer than another to fit. If your data set is very large, you would say, okay, well, I can do some distributed storage and computing. I can use Spark, I can use Ray, or I can use some other system that handles the distributed part of fitting a model, right? And so what I want to do is give you a big old diagram to end the modeling part of the class. So again, here we go. We have a sample, and now you know. We can split it up into a training set and a test set. Take that training set. You have a bunch of models you can try, and what you can do is check the models on the training set. You can also augment the models by tuning their hyperparameters, so you can choose a regularization. You can choose L1 regularization, L2 regularization. You can tune the lambda. You can tune the learning rate for gradient descent. You can tune the number of trees in a random forest. You can tune the number of nearest neighbors in a nearest neighbor classifier. All these things we call hyperparameters. And you can augment your model by performing some feature engineering before you fit your model on the data. Once you've fitted your models, you can then use cross-validation to decide on your chosen model. Dang it. There it is. So you can use cross-validation to decide on the model of choice by picking the one that has the lowest validation error. So out of all the choices here, you pick one using cross-validation. You give that model your test set, and that produces for you the test error. And you can do a bootstrap to compute a confidence interval for that test error. So all of these things you will have no idea how to do, or maybe you have some idea, but if you hadn't taken any modeling before, this diagram would have made no sense to you a few weeks before today. But now that we're in this part of the class, I can show you this diagram, and even if it doesn't make complete sense to you, you can at least smile at me and say, yes, I understand. All right, well, that concludes today's lecture, and I'll see you tomorrow for our last lecture of 100. Thanks.